Number 10. Closed-loop life support that actually works for centuries. Every space mission humanity has ever flown relies on resupply from Earth. The International Space Station gets regular cargo deliveries, carrying food, water, replacement parts, air-scrubbing chemicals. Take away that umbilical cord, and every crew that has ever lived in space would have died within months. An interstellar mission changes the math so completely it almost breaks your brain. The nearest star system, Alpha Centauri, sits roughly 4.2 light-years away. Even at speeds we will discuss later in this list, any realistic mission takes decades at minimum, and more likely, centuries. That means a life support system that recycles nearly 100% of everything. Water, air, nutrients from human waste, carbon dioxide back into breathable oxygen, every calorie of food grown on board from scratch. NASA's current best closed-loop systems on the ISS recycle about 93% of water from urine and atmospheric moisture. That sounds impressive until you realize that missing 7% compounded daily over a 200-year voyage represents an impossible deficit. Even 1% daily loss would drain a ship's water supply within years. The biological challenge is that ecosystems are not machines. They drift, they evolve, microbes mutate, nutrient cycles get imbalanced. We have never maintained a stable closed ecological system for more than a few years in controlled experiments. Biosphere 2 in Arizona, probably the most ambitious attempt ever, collapsed into chaos within 2 years. We are talking about engineering something 100 times more robust than anything ever attempted and keeping it stable across multiple human generations. Realistically, we are 50 to 100 years from even having a prototype that could survive a decade without outside intervention. Number 9. Propulsion capable of reaching at least 1% of light speed. 1% of light speed sounds modest. It is actually 3,000 kilometers per second, which is about 10,000 times faster than the fastest spacecraft ever launched. The Voyager probes, our most distant human-made objects, travel at roughly 17 kilometers per second. At Voyager speed, reaching Alpha Centauri would take 75,000 years. To make interstellar travel happen within a human lifetime, or even within 10 generations, you need propulsion that does not exist in any working form. Chemical rockets are immediately out. They are thermodynamically incapable of approaching those velocities. The most credible serious proposals include nuclear pulse propulsion, where a spacecraft rides the shockwaves of sequential nuclear explosions detonated behind it, laser sail concepts where powerful lasers push an ultra-thin reflective sail, and fusion drives that use the same reaction powering the sun. The Breakthrough Starshot initiative has genuinely explored laser sail concepts for tiny probes, but scaling that to carry humans introduces mass requirements that seem insurmountable with current engineering. Nuclear fusion propulsion is probably the most viable path for a crewed mission, but we have been promising controlled fusion for 60 years without delivering it commercially. The fundamental problem is the rocket equation. The more fuel you carry, the more mass you have, and the more energy you need to accelerate that mass, which requires more fuel. At interstellar scales, this becomes brutally self-defeating. We are likely a minimum of 100 to 200 years from tested propulsion that could credibly accelerate a crewed interstellar vessel to meaningful fractions of light speed. Number 8. Radiation shielding for interstellar space. Inside our solar system, the sun generates a magnetic bubble called the heliosphere that deflects a substantial portion of cosmic radiation. Once a ship leaves that bubble, it enters the unfiltered interstellar medium, which is bombarded with galactic cosmic rays. These are high-energy particles traveling at significant fractions of light speed themselves, and they punch straight through conventional shielding. More material between you and the radiation just means more secondary radiation, as particles strike shielding atoms and create new particle cascades. Astronauts on the ISS receive radiation doses roughly equivalent to 10 chest X-rays per day. In interstellar space, without the heliosphere's protection, that number climbs dramatically. Over decades or centuries, this exposure would cause catastrophic cancer rates, radiation-induced cognitive decline, and genetic damage that would compromise any attempt to establish a healthy founding population. Active magnetic shielding, essentially a miniature magnetosphere generated by superconducting coils around the ship, is the most promising theoretical solution. But generating and maintaining a strong enough magnetic field for centuries requires power and engineering far beyond anything demonstrated. Superconducting technology would need to operate without failure for the entire voyage duration. Material science improvements and breakthroughs in high-temperature superconductors are moving this forward slowly. Realistic timeline. A functional prototype design is probably 75 to 150 years away. Number 7. Long-term metabolic slowdown in humans. Movies make this look easy. People climb into pods, fall asleep, and wake up decades later looking refreshed. Reality is far more complicated. The human body at normal temperature requires constant metabolic activity to stay healthy. Cooling the body significantly to reduce that metabolic rate causes ice crystals to form inside cells, which can damage them. Existing preservation techniques can protect small tissue samples, but scaling this up to an entire body requires carefully managing protective compounds in every cell and removing them safely afterward. No one has successfully revived a large mammal from extreme cold storage, and humans are even more complex. A more achievable short-term approach is torpor, a shallower metabolic slowdown, similar to some animals' hibernation, reducing metabolism without freezing. Researchers are exploring ways to induce torpor using specific drug combinations, and early animal studies show promise. However, extending torpor for decades or centuries is completely untested. Muscle and organ health over such long periods pose major challenges. Any technology capable of using this method for long-duration space missions is likely a century or two away from being practical. Number 6. Long-term embryo preservation for space missions. This concept is more theoretical, but considered by some researchers as a potential way to support interstellar colonization. Instead of sending adults across vast distances, a small caretaker team could travel alongside preserved embryos, potentially thousands, to maintain genetic diversity for a future population. The embryos are kept in advanced preservation units and would need to be safely nurtured after arrival, either by humans or automated systems. Preservation for long durations is challenging. One system failure could compromise the entire mission. Bringing the embryos to term at the destination would require highly sophisticated automated care. While embryo preservation works for short periods today, scaling it up for interstellar missions involves multiple technical hurdles that have yet to be solved. And then there is the ethical dimension of bringing humans into existence in a world they did not choose, raised by robots or a tiny aging crew on an alien world. The engineering piece is perhaps 200 years out. The ethical and social frameworks to even decide whether this is acceptable are on clear timescale entirely. Number 5. Multigenerational governance and social stability systems. This is the one engineers hate talking about because it is not a hardware problem. Consider a generation ship with 1,000 people aboard, launched on a 200-year journey. The people who arrive at the destination share nothing in common with the people who launched except genetics. They were born on the ship, they will die on the ship without ever seeing a planet, and they had absolutely no say in the mission that defines their entire existence. History suggests that isolated human groups with absolute resource scarcity and no outside authority tend toward social breakdown, religious extremism, authoritarianism, or outright violence. What governance structure remains legitimate across 5 or 6 generations? How do you prevent the 3rd generation from simply deciding to turn the ship around? How do you distribute resources fairly when your survival depends on cooperation, but human tribalism is deeply hardwired? Political scientists and anthropologists who have engaged seriously with this problem note that we have essentially no successful models. Small, isolated communities on Earth have access to trade, migration, outside conflict resolution, and cultural exchange with the broader world. A generation ship has none of those pressure valves. This is not a technology problem that gets solved in a lab. It requires social experimentation, political theory development, and possibly some form of enforced social programming that raises its own serious ethical concerns. Timeline, genuinely unknown. Number 4. Autonomous repair and manufacturing systems. A ship that travels for 200 years will experience mechanical failure. Components will fail, systems will degrade, materials will fatigue in ways that even the best engineering cannot fully predict across that timescale. You cannot carry every possible replacement part for every possible system. The mass cost would be prohibitive. What you need is a system capable of diagnosing any failure, fabricating replacement components from raw materials, and executing complex repairs without human expertise that may not exist generations into the voyage. This points toward advanced artificial intelligence, combined with sophisticated manufacturing that goes far beyond current 3-dimensional printing. You need systems that can work with metals, ceramics, biological components, electronic systems, and novel materials, all autonomously and with the judgment to prioritize correctly when multiple failures compete for limited repair capacity. Today's AI cannot reliably repair a simple household appliance without human oversight. The leap to fully autonomous ship-wide repair management across centuries is staggering. A reasonable estimate puts genuinely capable autonomous manufacturing at somewhere between 50 and 150 years away. But the interstellar-grade reliability requirements push that further. Number 3. Artificial gravity systems. Long-duration microgravity destroys the human body. Bone density loss, cardiovascular deconditioning, vision problems from intracranial pressure, and immune system dysfunction all occur within months. Astronauts returning from 6-month ISS missions require extensive rehabilitation. Scale that to a decades-long or century-long voyage, and the result is a population that could not function upon arrival. The only proven method for generating artificial gravity is rotation, spinning a section of the ship to create centrifugal force that mimics gravitational pull. The engineering challenges involve the size of the rotating section, the Coriolis effects that cause disorientation at small radii, and the mechanical complexity of rotating massive structures reliably for centuries. A theoretical electromagnetic or gravitational manipulation approach has essentially no scientific backing in current physics. Rotation-based artificial gravity is buildable in principle, but has never been tested at meaningful scale for long durations. This technology is probably 40 to 80 years from a tested design. Number 2. Interstellar navigation and communication systems. At interstellar distances, radio signals traveling at light speed take years to arrive. A ship 4 light-years from Earth sends a distress call and waits over 8 years for a response. Navigation using stellar reference points at those distances involves measurement precision we do not currently possess, and any slight trajectory error undetected for decades compounds into arriving at the wrong location entirely. A quantum entanglement communication system that operates instantaneously regardless of distance would be transformative, but current physics suggests this is either impossible or operating through mechanisms we fundamentally do not yet understand. Navigation systems would need to autonomously correct trajectory across decades using reference stars while accounting for gravitational influences along the route. These systems require computational capability and sensor precision far beyond what is demonstrated today. Realistic timeline for adequate navigation systems is approximately 100 years, though communication remains deeply uncertain. A reason compelling enough to make humanity actually do this is not a joke. Every technology on this list is solvable given sufficient time, resources, and concentrated human effort. The Apollo program accomplished something that looked impossible in just 8 years because the geopolitical pressure made it a civilization-level priority. Interstellar travel requires something similar, sustained not for 8 years, but potentially for 200 years across dozens of political cycles, governments, economic collapses, and shifting cultural priorities. The philosophy of long-term civilizational thinking, the ability to commit resources now for payoffs that arrive long after everyone making the commitment is dead, may be the hardest technology of all to develop. We have never demonstrated it at civilizational scale. Realistically, this particular challenge has no measurable timeline at all. It depends entirely on whether humanity develops the maturity to plan beyond the next election cycle. Every item on this list is theoretically possible. None of them are close. The honest assessment is that a genuinely viable interstellar mission is probably 300 to 500 years away at minimum, assuming continued technological progress and no civilizational setbacks. Subscribe for the next video.